Yihong Wu, Professor Wu, comes from the Chinese Academy of Science. So she will be focusing on the SLAM topic using deep learning today. So I give the floor to Professor Wu. Welcome, Professor Wu, to give the speech. Thank you.
Hello, everyone. It's my pleasure here to have this presentation. Thanks to all the organizers. What's visual localization? That is to compute locations from images or videos. The contents are as follows. The first part is an overview of visual localization with learning. Then I introduce 3 parts of our work. Finally, it's a future work analysis. Please look at the first part of an overview of visual localization with learning and how we use learning in our visual localization. 3D vision is very important. In computer vision, the main tasks include 3D reconstruction, visual localization, SLAM. They have wide applications such as in AR, VR, robotics, and automated driving. Since Mars theory was proposed in 1980s, 3D computer vision had a blooming age in 1990s. In 2000, 3D vision was gradually well established. After 28, 3D vision applications went into people's daily life. The example is the movie Avatar was projected hotly in the world. Recently, 3D vision is reblooming with deep learning. After the Mars vision framework's establishment in 1980s until 2010, Thomas Pogge made a supplement for the framework. He adds a higher level beyond the computational level, that is the learning. In the Mars framework, the main tasks are to compute geometric shape and localization. After Thomas Pogge's supplement and AlexNet's good performance in ImageNet, 3D vision also entered into a deep learning age. At present, more and more deep learning methods are appearing in 3D vision. They include 2 kinds. One kind is an end-to-end method, and the other is still under the Mars framework with using deep learning in some modules. After more than 30 years of development, the robustness of computer vision has not been well solved. The reasons of robustness are as follows. At first, we should make an image feature extraction when making 3D reconstruction and localization. Then, if the configuration of camera and scene is degenerate, the computing result is not good, no matter how good the image feature extraction is. Otherwise, the computing result is dependent on the image feature extraction. Therefore, the robustness is determined by whether the image feature is good or not, and whether the configuration of camera and scene is degenerate or not. Now, please look at the superiority of deep learning. It has strong ability to extract image features and strong ability to handle degeneracy with data driving, while it has superiority on semantic reconstruction. These abilities just can solve the robustness problems of traditional methods. Therefore, we embed the deep learning into our traditional framework to solve non-robustness problem of visual localization. However, visual localization usually is performed on moving platforms and requires faster speed and lower power consumption. The usual deep learning methods cannot meet well the requirement. Okay, now let's look at the first hour work for visual localization. For solving the robustness problem at the same time, we consider the power consumption. One of the visual localization tasks is the long-term localization. At present, there are the following three groups of the methods. The first one is the image retrieval-based ones. The good performing methods are mainly the deep learning methods because the used features usually are the whole image CNN feature. They are not robust to images with larger view angle change and larger similar texture occupation. The second one is the 2D to 3D correspondence methods. They are usually not robust to larger illumination change. Deep learning methods can solve the problem, but they are usually slow and with larger power consumption. Binarization can solve the problem, but a straightforward way of binarizing decreases the accuracy greatly. The third method are the fusion of image retrieval based and the 2D to 3D correspondences. Usually the fusion is serial, that is at first making image retrieval and then making 2D to 3D correspondences. The first step usually limits the scope of the second step, and then such fusion cannot give the higher accuracy. To solve these problems, we give deep learning methods for local descriptors. We make random trees and binary descriptors for higher speed. We co-tree both real and binary descriptors for higher accuracy. We search nearest neighbor candidates of a given query local feature by both local and global descriptors in parallel, not in serial, for higher accuracy. That are robust to both the viewpoint change and illumination change. This is an overview of the proposed parallel framework. The first line is to establish random trees with local CNN features, where the leaf nodes store the 3D points. The below line is to make image retrieval by the whole CNN features. All the results are together to make a 2D to 3D correspondences. Please look at the local CNN features. We will have an image. The image feature points and patches enclosing the points are extracted at first. Then we construct a CNN network to make feature point description. The desired network is shown here. The backbone has 4 stages by adding, Let's shut up the WeChat. I'm sorry.
Okay, no problem.
Okay, it's closed the WeChat.
Yeah, okay.
The desired network is shown here. The backbone has 4 stages by adding shortcut connections. Since the patch is smaller, the network is not so deep. Therefore, the parameters needing to compute are less. The computation is of lower power consumption. This shows the loss function. There are in total three terms in the loss function. The first is the triplet margin loss. The second is the second order similarity regularization. The third is the weighted having distance for training binary values. This loss function co-trees real and binary values called CRB-net. The binary descriptors are lightweight and at the same time with higher accuracy, therefore the computation is lower power consumption. This show the testing result on public dataset. The above is the result for the real values. We see the CRB-net's good performance. The below part show the result for the binary values. We also see the CRB-net competitive performance. This is the result on HPatch's dataset. The most bottom line is the CRB-net performance, showing the best performance. After obtaining CRB-net, we train random trees. CRB-net descriptors of 3D points are used. By this training function, we concentrate 3D points where they go along the path. Finally, 3D points are stored into leaf nodes, and we obtain some random numbers for each tree. After giving a query local feature descriptors of CRB-net, binary descriptors of CRB-net, or this is a query feature, then we search the leaf nodes with the maximum probability of containing the nearest neighbor for this point to establish 2D to 3D correspondences. Then we perform a linear search in the leaf nodes by the real valued form of CRB-net. Therefore, we use both binary and real values of the CRB-net. Giving a query local feature descriptors CRB-net, then we can fast search the correspondences in 3D 3D space. By the correspondences, we can make a localization. This shows a testing result on a public result. On a public data set, the best result are in bold. The second performance are in red. The best in black. The red are in the second are in red. This is on another data set. Similarly, we'll see the CRB-net's performance and the parallel search framework. This shows the visual localization result. Even we only use the local descriptors, that is the first line the result. We see that the result is not good on the low illumination, but good on the large visual angle change. If we use global CNN features, the result is good on the low illumination, but is not good on the large visual angle change. But if we use the proposed parallel framework and our binary descriptors, all cases are good. Now, I'd like to introduce our second work, a flexible and efficient loop closure detection based on motion knowledge with thin hashing codes for a SLAM system. A SLAM system needs a loop closure detection for reduction of long-term error drift. The current problems for loop closure detection are as follows. Deep learning methods are usually used for higher robustness, but they are low speed and needs heavy labeling data. The second challenge is that there are dynamic objects in the scene making a color. The third problem is that if scenes are full of similar or repetitive textures, the detection will fail. In order to solve this problem, we propose deep supervised hashing for place recognition with lower power consumption, and we use both global and local features to solve the dynamic objects query problem. Simultaneously, we use multi-frames or videos to solve repetitive textures problem. We propose self-supervised hashing network without head labeling, and it can run in real time. We use deep learning feature and handcrafted feature theory to make a loop closure detection. And then we make pose optimization to decrease error drift. This is an overview of end-to-end manner to learn hashing code for place recognition. The input are the query image, positive image, and negative image. Then we use a lightweight CNN, such as MobileNet or GhostNet, to obtain features. After that, we use a fully connected layer to construct hashing binary codes. Finally, it connects the loss function. The loss function is as follows. There are two items in the loss function. The first term is a summation of 4 terms. They are respectively in these forms. The second term is a constraint for maximizing sum of squared errors between BI and 0.5. Makes the codes approach to either to 0 or to 1. This slide shows the overview of the loop closure detection for SLAM system. The module A is just the place recognition introduced above. The second module uses local features based on GMS to make a geometric verification and use a temporal consistency check within 2 frames. In the module C, that is in this module, after a period, local feature matching is performed. We constructed our own data set. There are 10 sequences, 4 indoor scenes and 6 outdoor scenes. In this data, there are in total 100,000 frames, of which 2,306 indoor frames and 4,517 outdoor frames are for training, and the left are used for testing. We will see a good generalization ability of our framework. In the scene, there are moving people and with weak textures like this, such as the scenes shown by these pictures. Also, there are images with view angle change, and images with repetitive textures. Please look at the picture shows the situations. The proposed place recognition was tested on the public data set and also compared with AlexNet features and S=SLAM. The results show that the proposed method has higher accuracy. The recognition pre-series are larger than 90%. This slide shows the testing result of the proposed loop closure detection on a public dataset. We see that the proposed method ranks the first on two dataset and ranks the second on the other two dataset. Also, we see that this method is the most stable way. We see this is the most stable way. For the first rank on this two dataset, we see that the very low precision on the other dataset. This slide shows the testing result of the proposed loop closure detection is time consumption. Due to its lightweight, the proposed method can run in real time in this speed millisecond. This shows the by the loop closure detection, we make a post-error drift correction. For the most videos, the errors are within 2 pixels. The time consumption, we can see that the result can also attain a real-time speed. This slide shows the difference between the location of the camera without loop closure detection and the result with the proposed loop closure detection and the error correction. We see that on the closure point, error is decreased greatly. The green curve is the location with the loop closure detection and the error drift correction. The red curve is not to use the loop closure detection. Now I'd like to talk about the third work, a robust PL SLAM system with accurate and fast tracking. We go to solve the robustness problem of the images with weak texture, motion blur, and illumination change. A SLAM or a VIO system system usually cannot work well in the environments with these situations. We use line and point features together to solve this problem. Another problem we go to solve is that the line segment tracking the problem. The general line tracking methods use line descriptors. Usually this way is very slow, that cannot have a real-time speed.
Ms. Wu, Professor Wu, if we can speed up as conscious of time, that would be great. Thank you.
Okay, I know. The proposed solutions are as follows. At first, we propose a hybrid point-line-based VLO framework, where point-line with shorter tracks are categorized into MSCKI features and with longer tracks into SLAM features. Especially, SLAM lines are added into the state vector to improve accuracy of the proposed system. This shows the minimization of the proposed method. This is a testing result that shows the not only higher accuracy and the faster speed. We also compare our method with popular and famous SLAM or VIO systems. The result also shows the best performance. We see that the relocalization comparison with the ORB SLAM 3. This is the testing result on a repetitive texture. Finally, I make a conclusion. I talked the 3 items of our work. The first one is co-training real and binary single descriptors for SLAM relocalization. The second is an efficient loop closure detection with single hashing codes. The third is a SLAM system with accurate and fast line tracking. In the future, we still go to solve SLAM the challenges with deep learning by considering low power consumption, robustness, accuracy, speed at the same time. That's all my talk. Thanks.
Great. Great. Thank you. Thank you, Professor Wu.
We want to thank especially our strategic partners who have made it possible. We have our executive sponsors, ARM, the Software and Hardware Foundation for tinyML, then at Impulse tinyML for all developers, Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous, Sentient end-to-end deep learning solutions for tinyML and Edge AI, then Platinum sponsors, Reality AI, add advanced sensing to your product with Edge AI, tinyML, and then Renaissance, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge, Maxim Integrated, enabling edge intelligence, Seed Studio, the IoT hardware enabler, SensiML, build smart IoT sensor devices from data, SynSense, build sensing and inference hardware for ultra-low power embedded mobile and edge devices, and our silver sponsors, Aeon Devices, Deep Light, EMSA Visual Sense, Greenwaves Technologies, Gravity Inc., HODG, Imagimob, Kixo, Rixen Technology, and SAP. So thank you everyone for staying with us today, and see you tomorrow.